You should have learned the analytical differentiation in the calculus class, and you should know how to differentiate simple continuous functions such as the trigonometric function here, log function here, exponential function here, and so on. However, it's difficult or almost impossible for us to solve complicated functions like this case, as well as tabulated data in discrete format. In this study, we will extend the analytical differentiation to the numerical differentiation, which is useful to solve discrete data as well as complicated functions. By performing the analytical differentiation, you are actually looking the gradient or the slope at a particular point here. And at this point, the delta x is approximate to 0. We can find the gradient at this point by using the delta y divided by delta x. Take the limit delta x approximate to 0, then we can let this equal to the dy over dx. So in this case, the analytical solution has no error. So this is 100% accurate. The solution that you obtain here is exact solution. In practical, it is impossible to obtain the delta x approximate to 0 to calculate the differentiation. So in the numerical study, we set a finite value for the delta x. So in this case, delta x is our step size. Theoretically, the gradient should be tangent to the path here, and if we use the numerical approach, we set the delta x to be a finite value here, delta y divided by the delta x, and take the delta x equal to 0.1 in this case. When you calculate this, then you obtain the derivative solution. This solution is approximation to the dy over dx. The approximation here is close to the actual gradient, therefore we say it is a good approximation. However, if you choose a large step size, in this case, then by computing the delta y divided by delta x, and in this case you choose the delta x equal to 5, so after you compute this, you found that the approximation is not equal to the dy over dx. Where you can see the approximation here is far away from the actual gradient. Therefore, it's very important to choose a suitable step size in numerical study. Wrong selection of this will cause bad approximation. Before we move to numerical algorithm for the differentiation, let's look at the non-computer method or the manual calculation for the differentiation. You are given a discrete data in a table format, and you want to know what is the dy over dx at this 6 point. In this case, we can approximate the derivative by using delta y over delta x, where we select the delta x equal to 3 minus 0, we obtain 3 here. And you can also find the delta y between these 2 points by taking 200 minus with 0. Therefore, you obtain 200 here. Take 200 divided by 3, you should obtain the delta y over delta x equal to 66.7. And you can repeat for the next 2 points here. So this is delta x by taking 6 minus 3. So you can obtain delta y by taking 350 minus 200. So divide it with delta x, then you obtain it. Continue with the next 2 points, compute the delta y and delta x here, and divide between them, you should obtain this answer. Continue with next 2 points here. So take the delta y here, minus with delta x, you obtain another solution. And lastly, take the delta y divided by delta x here, you obtain this solution. Then, plot the delta y over delta x versus the x here. So you can obtain the x value from here, which is from 0 to 18. From 0 to 3, you have 66.7, which is here. 3 to 6, you have 50, which is here. 6 to 9, you have 40. 9 to 15, you have 30. Lastly, 15 to 18, you have 23.3. Then you plot a curve at the middle point of each bar here. This curve is plotted by carefully balance the area for each bar here. Then from this curve, you can obtain the dy over dx result at this 6 point. So these are the results for the first 2 points. You have the dy over dx approximate to the delta y over delta x here, which is equal to 76.5. For the next point at x equal to 3 here, from the graph you read it around 57.5. Therefore, your dy over dx is approximate to delta y over delta x here. Then you should obtain this answer. Continue read the delta y over delta x for these 4 points. So the next point will be here, 4th point will be here, 5th point will be here, and last point will be here. Then you success to obtain the dy over dx, which is the derivation from the raw data here. We can perform the numerical difference by using the finite divided difference. You should have learned this before. We have 3 types of the finite divided difference. First type is the forward type, second type is backward, third type is center type. To find the first derivative at the xi, which is over here, then you can find the true derivative at this point by using the tangent curve here. In the forward finite difference method, we are using the forward point here to estimate the gradient. The forward point is at xi plus 1. Therefore, you can obtain the step size, which is h symbol here, equal to xi plus 1 minus with xi. And you can find the delta y here equal to fxi plus 1 minus with fxi. Therefore, the first derivative of the xi is equal to the delta y divided by delta x, or the h symbol. And for this method, the error is quantified by this term, which is OH. For the backward finite difference method, then you use the backward point, which is the xi minus 1 to compute the gradient. So you have the step size here to be h, and then delta y here to be fxi minus with fxi minus 1. This method has the same accuracy as the forward method, which has the error equal to OH. Compared to the forward and backward type of finite divided difference, center finite divided difference use the forward and backward point to estimate the gradient at xi here. In this case, the delta x is equal to 2h, which is equal to xi plus 1 minus with xi minus 1. And the delta y here is equal to fxi plus 1 minus with fxi minus 1. The approximation result for the derivative is close to the actual solution here. Therefore, the center finite divided difference method is more accurate compared to the forward and backward method. For this method, you have the error equal to OH squared. Bear in your mind, the forward and backward finite divided difference has the accuracy level equal to OH, and the center finite divided difference has the accuracy level equal to OH squared. For the first 2 methods, you have the error proportional to the step size. When you reduce the step size, let's say reduce half of it, then the error computed by the forward and backward method will be reduced by 2 as well. On the other hand, for the center method, the error OH squared here is proportional to h squared. Since you have power of 2 here, therefore you obtain h squared divided by 4. And in the error here, it will be reduced by 4 times. For the same reduction rate for the step size, the error for the OH2 reduces faster than the OH. Therefore, the center method with OH2 can give us more accurate result. This is the example that you solved before. The fx function is given, and you are going to find the f prime at x equal to 0.5. And we are going to find the derivative by using the forward, backward, and the center finite divided difference method. So in this case, we are using the step size h equal to 0.5. So in this case, you have the xi equal to 0.5 here. Substitute inside this function, you obtain your fxi here to be 0.925. By using the forward method, you need the forward point here at xi plus 1. Since the step size is given 0.5 here, therefore your xi plus 1 is equal to 1. Substitute the 1 inside this function, you obtain f1 equal to 0.2. Then you can find the step size here to be 0.5. Then find the delta y here to be 0.2 minus with 0.925. Then you should obtain the delta y divided by delta x to be this formula. And after you calculate, you should obtain the derivative equal to this answer. And if you compare to the actual answer, the error is equal to 58.9%. For the backward method, you need the backward point here, which is at 0, to find the answer. Substitute the 0 inside this function, you obtain your f0 equal to 1.2. The step size here is still 0.5, and the delta y here is equal to f0.5, which is 0.925 here, minus with 1.2. Take the delta y divided by delta x, then you can obtain the derivative result, and this is the corresponding error. For the center finite-divided-difference method, you need the forward and backward point here to estimate the derivative f prime at x equal to 0.5. So you can compute the delta y here by taking the f1 here minus with f0 here, which is equal to this. And then the step size here is equal to 1 minus 0, which gives you 1. Take the delta y divided by delta x, then you can obtain the approximation result. And this is the corresponding error. When you compare to this error, you see this is the lowest error. Therefore, we can say that the center method is the most accurate method compared to the forward and backward method. You have learned how to perform the forward finite-divided-difference by using this formula to compute the first derivative. This method has the accuracy level equal to OH. Besides that, we can improve the algorithm by incorporate more terms of the Taylor series expansion, which means we increase the order of the method. By doing this, the accuracy level for the method will be increased to OH squared. So you have two formulas here to compute the first derivative. Second formula is more accurate because the error is OH squared. For the first formula, you only need one forward point to compute the derivative. However, for the second formula, you need two forward points to compute the derivative. Not only the first derivative, we can also perform second, third, and fourth derivative by using the equation here. For the backward finite-divided-difference method, previously we are using the first formula here. Besides using this formula to compute the first derivative, we can also perform this formula to compute it. This formula is more accurate because the error is equal to OH squared compared to the OH here. So for the first formula, you need one backward point to compute the first derivative. For this formula, we need two backward points here to compute the derivative. Besides that, you can also refer to this formula for the second, third, and fourth derivative computation. For the center finite-divided-difference case, previously we are using this formula to compute the first derivative, and we know that this formula has the error equal to OH squared. We can improve this formula by incorporate more Taylor series expansion, which means increase the order to obtain this formula. By doing this, we can improve the accuracy of the solution. Therefore, you obtain the error equal to OH power 4. For this new formulation, you need two forward points and two backward points to compute the first derivative. Besides that, the formula to compute the second, third, and fourth derivative are provided here as well. Let's try with this example. So you have the same fx function as the previous example, and you want to find the f prime x when the x is equal to 0.5. So you want to find the first derivative when x is equal to 0.5. Therefore, we let the xi equal to 0.5. Substitute 0.5 into this function, then you can obtain f0.5 equal to this answer. Since the step size is given 0.25, so 0.5 plus the step size, you obtain 0.75. So this is the forward point. Take the xi minus with the step size, then you obtain the backward point equal to 0.25. Substitute these two values inside this function, then you can obtain the corresponding fx function. By using these three sets of discrete data and perform the forward backward and center finite divided difference by using these three equations, then you should be able to obtain the estimation for first derivative to be these three answers. We can improve this algorithm by incorporate the higher order method. These three formulas are known as the forward, backward and center difference method with the accuracy OH squared and OH power 4. To implement this formula, you need additional data at xi plus 2 here and xi minus 2. 0.75 plus the step size, you obtain 1. So this is your xi plus 2. 0.25 here minus with the step size, then you obtain 0. So this is xi minus 2. Substitute these 2 points into the function here, then you obtain the corresponding fx. So let's substitute inside this formula. H is 0.25 for these three formulas. Substitute 0.925 to the fxi function here. Substitute the forward 2 points to the forward formula and the center formula here. Lastly, substitute the backward 2 points to the backward formula and the center formula here. Perform the calculation, then you should obtain these three results. As you can see, the error that you obtain from these three formulas is much lower compared to the previous error. Therefore, we can say that this three formula has a better accuracy compared to the previous formula. Center finite difference method here gives the best accuracy as the error is equal to OH power 4.